Hello, this is question 16 on your AQA paper 1 from June 2019. You have this function here, and we have to find just the derivative, and we have to simplify the answer. So remember to find the derivative when I have a function multiplied by another function, we can use the product rule. So I'm going to differentiate this one multiplied by this one plus this one multiplied by the derivative of this one. Yeah, so if I have that my function is u v, so a function u and a function v, my derivative is going to be this thing here. So I derivate each at a time. Derivative of e to the power of minus x, so dy by dx is going to be minus e to the power of minus x. And then I copy the rest of the function, so the second factor, without doing anything. And then I plus the first function, and I differentiate the second factor. Derivative of sine is cos, derivative of cos is minus sine. And now what I'm going to do is to expand the brackets and simplify. So when I expand the brackets, I have this multiplied by sine x, then minus e to the power of minus x cos x, plus e to the power of minus x cos x, minus e to the power of minus x sine x. I'm just expanding brackets. And now I have these two are gone, and I have two that are equal. So minus 2 e to the power of minus x sine x. So that's my derivative, and I cannot simplify more. You could put this in the denominator if you prefer, but nothing else that you can do really. Then for b is say hence, so we are going to use this information here in the first part of the question, so that the integral of e to the power of x sine x, e to the power of minus x sine x is this function here. We know, because we have worked this part, that if we integrate this function, we get this one. And we have to integrate the same function, but without the minus 2. So the integral of this one is going to be the integral of this one, but just divided by minus 2. So the integral of e to the power of minus x sine x dx is going to be the same than the integral of this one, which is the original function divided by minus 2. So it's going to be minus a half e to the power of minus x sine x plus cos x plus my constant of integration. And a is a rational number, which is precisely what we got. Yeah, so a is minus a half. Just in case you can write it down. And that's part B. Then for C, we have something, we have to find the area. So we have a sketch of the graph, is this one. And the areas of the finite regions are called A1, A2, and so on. We have to find the exact value of A1. So to find the area of A1, so we need to find this area here, we are going to integrate our function, but we need to find the limits of integration. So this one is 0, the left one is 0, but we need to find this one. This one is the next time the graph cuts the x-axis. So the first one is at 0, and then we need to find the next one. So what we're going to do is just to make the function equal to 0 and see when that happens. The function that we are representing there is this one. So we are going to be careful, because this is slightly different than the original one. The original one has a plus cos. We are representing something slightly different. We don't have the cos. So we are going to make that function equal to 0 to find when that value happens. It's a product. This cannot be 0. So what is going to be 0 is sine x. Sine x is 0 when x is 0, and it's this value here, and the next one is when x is 180 or pi. I could use pi just because in the next part of the question they give us the angle in terms of pi, so they give the angle in radians. So I would use radians. This value is going to be pi, because if you check the question, they don't say anywhere anyways. So the exact area is going to be the integral of the function between 0 and pi. So e to the power of minus x sine x, sine x dx. And we know that this is going to be minus 1/2, so just because we did it here, minus 1/2 of e to the power of minus x, so all that we found before, e to the power of minus x, sine x cos x, sine x plus cos x. And we are going to find the values between 0 and pi. When we substitute pi, we have minus 1/2 e to the power of minus pi. So this is equal to minus 1/2 e to the power of minus pi, and just substituting the pi, then sine pi is 0, cos pi is minus 1. So times minus 1. And then minus, I'm going to substitute 0. E to the power of 0 is 1, so I have minus 1/2. And multiplying sine of 0 is 0, cos of 0 is 1. So times 1, I just leave the minus 1. And this is 1/2 e to the power of minus pi, minus minus plus 1/2. And if we can write something like this, e to the power of minus pi plus 1. It looks slightly better, but you can leave this form anyway. Yeah. So this is the exact value of A1. Next thing they ask is show that A2 divided by A1 is e to the power of minus pi. So for finding that fraction or that quotient, we have to find A2. A2 is the next area, is this area here. So we are going to find that A2, again integrating the function between pi and the next value that give us sine 0. Sine 0 is 2 pi. Yes? So we are going to integrate the function between pi and 2 pi. I'm just going to integrate it straight away. So that was minus 1/2, because we know the integral. It's just substituting the value. So sine x plus cos x between pi and 2 pi. And we are going to substitute. So when I substitute 2 pi, I have minus 1/2 e to the power of minus 2 pi. Sine 2 pi is 0, cos 2 pi is 1. So times 1, I'm not going to write anything. And then I substitute by pi. So I have minus 1/2 e to the power of minus pi. Sine pi is 0 and cos pi is minus 1. So this goes multiplied by minus 1. So I have minus 1/2 e to the power of minus 2 pi. And then 3 minuses is a minus 1/2 e to the power of minus pi. You can write this as minus 1/2 e to the power of minus 2 pi plus e to the power of minus pi. If you realize this is minus, and this is minus because this area is under the x-axis, so we get a negative integral, but the area cannot be negative, so be careful, because A2, the area, is that but positive, because the area must be positive. It's just the integral what is negative. And now we can find the division between A2 and A1. So A2 is this expression here, e minus 2 pi plus e minus pi divided by A1, that was, we have it here, e to the power of minus pi plus 1. E to the power of minus pi plus 1. And we have that this expression must be e to the power of minus pi. So we have to think a bit how we can simplify it. To start with, we can cancel the 1/2. We need to simplify somehow this with this. If you realize, we can divide both by e to the power of minus pi. So we can factorize that, getting the e to the power of minus pi outside. And we have e to the power of minus pi, because when we multiply, we have e to the power of minus 2 pi, and then plus 1. And now I'm going to be able to simplify these two and have e to the power of minus pi. So that's what I have to prove. Yeah, I have to show that a2 divided by a1 is this value here. Next thing it says, given that an plus 1 divided by an is always e to the power of minus pi, so a2 divided by a1, a3 divided by a2, and so on, we have to find the exact value of the total area enclosed between the curve and the x-axis. So we are going to add all these areas here. If you realize, really what this means is that if I have a1, a2, a3, and so on, if the fraction between a2 divided by 1 is e to the power of pi, that means I have multiplied by a to the power of minus pi. And I'm going to do that every time. Yeah, so if this is true, every time to find the next term, I'm multiplying by e to the power of minus pi, which means this is a geometric series because I'm multiplying by a constant. That's the common ratio. If I want to add all the values, what I'm going to do is the sum to infinity of my series, so of my areas. And remember, this is going to be a, so the first term divided by 1 minus r. And this is in your formula booklets. So for example, in the Excel 1, I don't have here the AQA, but you will have it. So this is the formula for sum to infinity. So a is the first term, and we say the first term is 1/2 e to the power of minus pi plus 1, that was a1, divided by 1 minus r. And r is the common difference, so e to the power of minus, the common ratio. This is quite similar to this one, but we have the e to the power of pi positive instead of negative. So what we can do is to work a bit with the expression until we have that. So the 1/2 can go at the front, and then instead of e to the power of minus pi, I'm going to write this. Yeah, so I'm going to bring it to the denominator. And I'm going to do the same with the other one. So I have 1 minus 1 e to the power of pi. And I'm going to add the fractions. So I have 1/2, and here I'm going to have 1 plus e to the power of pi, positive pi, divided by e to the power of pi. That's my numerator. And in the denominator, I have e to the power of pi minus 1 divided by e to the power of pi. Yeah, so I'm just adding this fraction, and this one, and this fraction, and this one. If we divide those two fractions, so if we divide this fraction by this fraction, this can be cancelled with this. And then I have 1/2 at the front. Numerator is e1 e to the power of pi, and denominator is e to the power of pi minus 1, which is what I have to prove. Yeah, and that's all. So I think the difficult bit here maybe is realizing that this is a geometric series, but other than that, it's just using the formula and work a bit with the expression. Yeah, and that's all with this question.